This is the video abstract for Engineering Bright Matter Wave Solitons of Dipolar Condensates by Matthew Edmonds, Thomas Bland, Ryan Doran and Nick Parker. Imagine dropping a stone onto a surface of water. A wave is created that travels outwards from where the stone breaks the surface. As the waves travel outwards from the source, they diminish and eventually vanish. We're used to seeing this behaviour of waves, however this is not the full story, as we will see. In our work, we model a phenomenon known as Bose-Einstein condensation, a state of matter realised in dilute gases of ultra-cold atoms as their temperature approaches absolute zero. In these systems, quantum mechanical rather than classical physics plays a dominant role in describing their behaviour. Analogously to the example of waves in water, Bose-Einstein condensates also behave like waves. Under special circumstances, these waves can retain their form and propagate over very long distances. These waves are termed solitons and have been observed in many physical systems, including Bose-Einstein condensates. Specifically, this work focuses on a particular type of condensate known as a dipolar condensate. Here, the atoms feel a type of magnetic interaction with each other, leading to novel properties as we will explore. Pictured is a cartoon of a dipolar condensate, where each arrow represents a direction of the magnetic force, all of which are in the same direction. They are polarized. To understand the behavior of solitons in this system, we looked at modelling their collisions. On the left, we can see the density profile of two initially separated solitons moving towards each other, and on the right, a line plot of their trajectories. In the first example with the green outline, the strength of the dipole interaction is weakest. We see the solitons collide, constructively interfere, and then move apart again. They have elastic dynamics with the same initial and final velocities. These elastic collisions are typical of how conventional non-dipolar solitons interact with each other. In the next example, with the orange outline, the strength of the dipole interaction is intermediate. In this regime, the dynamics of the solitons are more interesting. They stick together, forming what's termed a bound state. However, this behaviour is not stable, and eventually the solitons break apart and move away from one another. When the strength of the dipole interaction is increased further, as in the final example with the blue outline, we again see what appears to be a bound state forming. However, the solitons cannot escape as before. In fact, they have fused together, exhibiting truly inelastic behaviour. Solitons owe their existence to their balance between their kinetic energy and their interaction energy. The dipolar bright solitons we studied exist in the presence of attractive interatom interactions. A consequence of this is that the soliton's wave packet can undergo an energetic collapse if the strength of this interaction exceeds a critical value. We calculated when the dipolar bright soliton would be stable and when it would be expected to collapse. The horizontal axis gives the strength of the dipoles, whilst the vertical axis gives the strength of the van der Waals interactions. By varying these two quantities, the full phase diagram stability can be computed. The red lines indicate the boundaries between the stable and unstable areas, while the blue shading gives the aspect ratio of the soliton, a measure for how three-dimensional it is. For example, in the dark blue regions, the soliton is extremely elongated, while in the lighter blue regions, the condensate has a more three-dimensional character. Thank you for watching.